Okay, so this week's speaker is Pranjal Nayak. He's a postdoc at the University of Geneva and an old friend, and he's going to tell us about ergodicity and thermalization in low-dimensional theories.
Hi everyone. Thanks for inviting me to present this talk today. I think this is a very nice initiative, especially in these times when it's really hard for people to meet in general. So I hope to be able to be a little more involved with the whole thing from now on. But so so and my talk seems to be a good place to start for myself. So. Today I'll be talking on ergodicity and thermalization in low dimensional theories, which is based on some work that I have done with my collaborators Julian Sonner and Manuel Velma over the past couple of years, and some ongoing work with the same collaborators along with Alex Atlan that should come out within next month or something. So the fundamental motivation behind our work is rather elementary. We want to understand how is it that a unitary quantum system, uh, which has unitary evolution and unitary time dynamics, gives rise to thermal physics in some sort of classical limit. And we also hope that our improved understanding of this question would also help us understand the questions about black hole formation using the ADS-CFT correspondence. And in today's talk, we would basically try to understand some of these questions using a simpler model of which is known as the SYK model. So while this stays like our big motivation in working towards understanding thermalization better, my today's talk would be focused on a part of this bigger question, which is to understand quantum chaos. Uh, so the linearity of quantum mechanics makes it impossible to generalize the classical notion of chaos, which is understood in terms of departing trajectories in the phase space. So once we start studying quantum mechanics, we need a different definition of quantum chaos, and historically there have been quite a few propositions for the same. One of them goes by the name of quantum ergodicity, which which basically compares the spectral statistics of what we want to show as a quantum chaotic system with that of random matrix theory, and the similarities of these spectral statistics with that of random matrix theory is is provided as a measure of quantum chaos in a quantum theory. Alternatively, there is a semi-classical definition which more closely generalizes the notion of departing trajectories uh, in a quantum system, which is through a measurement of some out-of-time ordered correlation functions and their exponential behavior. So, what we are really doing in our attempt to understand quantum chaos is following the classical old saying, which goes by that we are trying to kill one bird with two stones. So, let me start with briefly reviewing and telling you what each of these definitions are more precisely. So the quantum ergodicity conjecture is a conjecture by Berry and Tauber due to their some work in 70s, which states that in a quantum chaotic system, the spectral statistics are similar to those of random matrix theory. Now there are different classes of random matrix theories, and each of them have, like, if a physical quantum system has spectral statistics similar to any one of those class of random matrix theories, then that system is said to be chaotic. More precisely, such systems in classical limit uh, go back to systems which are classically chaotic. And this conjecture is mostly empirical. This is more empirically motivated. Okay. Uh, Also, a part of this conjecture states that the quantum integrable systems are those whose spectral statistics are described by those of Poisson statistics. So this is a precise conjecture which helps us.
Pranjal,
Yes.
Pavan and Nirmalya have questions. Like, please, guys, go ahead.
Yes. I'll one of them can go first,
Hi.
and the other one.
So, can you explain a bit more what random matrix theory and spectral statistical properties are?
Right. So random matrix theory is okay. Random matrix theory is a putative theory in which you consider a Hamiltonian which is randomly chosen. So each element of the Hamiltonian, which can be seen as a D by D matrix, is randomly chosen from some Gaussian ensemble. Okay, and this theory has been successfully used to describe disordered media where you don't know exactly where the impurities are. So the Hamiltonian precisely is not known. It has also been used to describe the Hamiltonian of nuclear system atoms with large nuclei. So this is random matrix theory is, like, in the simplest words, theory of a Hamiltonian where Hamiltonian itself is not known and therefore is randomly chosen from a Gaussian ensemble. And spectral statistics that I'm talking about here, which I'll describe more carefully as I proceed in my talk, is the P of omega here that is a particular spectral statistic which measures what is the distance of the next nearest neighbor. So the omega here is the distance, the energy gap between a given state and its next nearest neighbor. And the plots that I'm showing here describes the probability of finding a physical eigenstate of the Hamiltonian at a given energy. So it's a P of omega versus omega plot. The other spectral statistics that I'll be talking about is basically correlation functions of the density of states. So density of states for a random matrix theory is something which is continuous, unlike so if you have a d-dimensional Hamiltonian, you know that there are d eigenvalues, which there some of which might be degenerate, but in general there are like discrete eigenvalues. But when you sum over the Hamiltonian using this Gaussian ensemble in a random matrix theory, then the density of the spread of the eigenvalues becomes continuous, and and therefore the density of states is given by some continuous function. And if you look at the correlation functions between the density of states between different realizations of the Hamiltonian, then that also provides us an interesting spectral statistic. Okay, was I clear here?
Yes.
Okay.
Lata have question. Parijat, you can go ahead with your question.
So I have a question from your previous slide. So how do you define the departing trajectories?
In this one,
Yes.
like departing trajectories are defined only for a classical system, and in a quantum system there is no notion of trajectories, so I don't really define departing trajectories for a quantum system.
Okay. Thanks.
What I'll define is an out of time ordered correlation, and like in just a couple of slides, I'll show how the notion of departing trajectories is really related to the notion of out of time ordered correlation.
Lata also has a question.
Mm-hmm.
Yeah, I have a question from the next slide. So I was asking that, yeah, you talk here about the chaotic system where it follows random matrix theory and then integrable system. But there is also this many-body localized phase which follows Poissonian statistics. So do you distinguish between that and integrable system, or you take them all together?
Right now, no, I don't. I don't distinguish between these two.
Okay.
That's a good point. Yeah.
Okay, thanks.
Thank you.
But just for my knowledge, is that different from the integrable system or not?
And right now we are interested more in systems which don't have many body localization.
Okay.
But I'm not sure if I would call that integrable per se. Yeah, I'm not sure.
Okay, thanks.
Are there any more questions? Okay, if not, then
I
I'll
think you can
go
proceed.
ahead. Okay. So one important aspect of the this particular, for example, spectral statistics that I'm showing presently on my slide is the level repulsion, which says that the probability of finding degenerate states or state in is zero for a quantum chaotic system, and this particular property will become important later in some of the other physical properties of in describing some of the other physical properties of a generic quantum chaotic system. Okay, so which is precisely this, that the level repulsion and spectral rigidity, which I'll describe what spectral rigidity is in a minute, are basically the spectral properties which leads to a very typical behavior of various observables in quantum chaotic systems, which is a very characteristic slope ramp plateau behavior of the observables like spectral form factor and correlation functions in a quantum chaotic theory. Okay, here the slope is like the initial decay is what I call the slope. The ramp is the linear growth that follows after a certain time, and the plateau is the final plateau of the value of observables. Okay, and so the spectral rigidity is basically the regime of energies, the omegas, for which the RMT behavior holds. So spectral rigidity is kind of a measure of the domain in which the spectrum of a physical quantum system resembles that of an RMT, and it is also known as the ergodic limit, precisely the limit in terms of the energies or time in which the RMT statistics make themselves manifest for a system of interest. And in terms of the physical time, this is the ergodic limit is closely related to the ramp time, which is precisely the time at which the initial slope, the decay, transitions into the ramp in the behavior of these observables. Okay. So now let me move on to reviewing the other definition of quantum chaos, which is related to the sensitivity of initial conditions. So the classical definition of quantum chaos, which basically says how the trajectories depart measures the deviation of the trajectories, which initially started close to each other, but after certain time t have exponentially deviated from each other. And you can see this can be written down as a classical Poisson bracket of the canonical coordinate at time t with canonical momentum at time 0. So Larkin and Ovshinnikov in 69 gave a quantum generalization of this definition in terms of square of a commutator of two arbitrary operators. To make a precise connection, you would say the operators are canonical momentum and canonical coordinate, but in general, you can work with any generic operator W of t and V of 0. And when you look at the commutator squared of these two operators in a thermal state, then for a quantum chaotic system, this particular function shows an exponential growth, which is what is conjectured to be related to the exponential growth of the classical trajectories. And this particular definition has been has been a subject of interest in last 5 or 6 years since the work of Stanford and Schenker, which gave it as a measure of which used it as a measure of quantum chaos for holographic quantum field theories. Okay, so just to summarize this initial discussion, what we have here are two seemingly distinct definitions of quantum chaos, and what we want to do through our work is try and understand what is the relationship between these two pictures of quantum chaos, and there's a second closely related question that we are interested in understanding, which is what can we say about thermalization within pure states of a quantum system. So this will form the main subject of my today's talk.
Pranjal, Prashant has a question.
Yes. Okay.
Hi. So in your earlier slide, in your first picture, can you just go back to that slide?
This one?
No, the one after this, where you showed the plots, Pn of omega.
Yeah.
So in this, just to understand, so you said that you have a Hamiltonian, which is not which is not well defined. Rather, you're drawing, you treat the Hamiltonian as a matrix, and you're drawing the elements of that matrix from a Gaussian. So, am I to understand that An and Bn are coming from the Gaussian, for example?
No. An and Bn, it's themselves are fixed numbers which come, which depend on. So I talked about various types of symmetry classes of the Hamiltonian. Basically there are 10 types of random matrix theory, and An and Bn depend on what type of random matrix theory you are working with.
Okay, so then, so suppose you take a particular, say, I don't know, realization of the Hamiltonian matrix, which I mean, you've drawn in a particular way, and you have a set of values. So that will give you a distribution of the eigenvalues, right?
Yes.
So,
yes.
Now you're saying that given a particular Hamiltonian, you are able to fix An and Bn depending on some classification. Is that
No. So there are two different things here. So one is I have a Hamiltonian within a symmetry class, which basically tells you what are the symmetries of the Hamiltonian. Okay, that symmetry class decides the An and Bn for you. Now within that symmetry class, you have a random matrix, like you have different realizations of your Hamiltonian. Okay, so the symmetry class decides basically like whether your Hamiltonian is Hermitian or it is real it has like whether you have to choose the elements of the Hamiltonian from complex numbers or real numbers, or whether it has chiral symmetry or whether it does not have chiral symmetry. So that decides the NNBN. And for each realization of the Hamiltonian within a particular class, in principle, you don't have smooth distributions like this, because a given realization of Hamiltonian will have some discrete set of eigenvalues and discrete eigenstates. Okay.
Right.
So there I can't plot things like this. I look at like various weighted averages of various realizations of the Hamiltonian. And then like when I average the behavior of the spectrum over these different realizations, then I get these smooth functions that I'm showing here.
I see. Okay, thanks. Also, sorry, I have another small question. Does this, when you say that you're drawing only from Gaussian ensembles, does this sort of limit, is this general enough, or like, I don't know, is that a...
So you could have more complicated ensembles, like you could have, add cubic and quartic terms to it, but to your ensemble average, like the weights. But in general, like how should I say it? In like the leading behavior comes from the quadratic part, because even when you have like the higher perturbation terms, you would in principle modify your potential in a way that it has say multiple minimas, for example, for a particular case, and then you can study like close around a particular minima. The leading behavior always comes as a Gaussian.
I see. Thanks.
Sorry, Pranjal.
So the non-Gaussianities, sorry.
No,
Can
go
I
on.
just complete?
Sure.
So the non-Gaussianities start playing roles when you start studying higher point functions of, for example, as I was talking previously, of the density of state. So if I look at two-point function of density of states, which is what I'll be mainly looking at today, you don't see these non-Gaussianities. But for higher point functions, these non-Gaussianities start playing more physical roles.
Sorry, Pranjal, I just wanted to just add that just as a sort of suggestion that since most of the people here are kind of used to working with field theory, so the way you defined your random matrix theory was as this: you take a Hamiltonian that's d-dimensional and d cross d matrix, and the Hamiltonian matrix has like elements that are sourced from like a random distribution.
Yes.
But
so,
from yeah.
I think, I'm sorry, I see where your question is going, but can you just wait one more slide? Maybe I might be talking about precisely what you're saying.
Okay.
So if not, after the remaining one more slide, then you can stop me again and we can, I'll explain it even a bit more.
Sure, yeah, okay.
So the is that I would start with a brief review of SYK model. So sorry, Madhu, maybe not one more slide, a few more slides. I'll come to that. Basically, I come to what you're asking in a minute. So I'll start with a brief review of the SYK model. And from there on, I will go on and discuss my ongoing work on the ergodic limit of the SYK model. Then I will briefly review Eigenstate thermalization hypothesis and a more generalized version of the same hypothesis, which I will further go on to study the Eigenstate thermalization hypothesis in the SYK model and insert in different limits of the SYK model, which I'll describe when I come to it, the Schwarzian sector and the conformal sector. And finally, I will give some final thoughts and conclude my talk. Okay, so let me start with a brief, really quick lightning review of the SYK model. So SYK model is a model of a large n number of Majorana fermions with an all-to-all coupling between all the fermions, such that these couplings are randomly chosen from a quench. Basically, which all that means is, that's a fancy way of saying that these couplings are randomly chosen from a Gaussian ensemble. So, for example, this here is a type of is the Hamiltonian of the SYK model with Q interactions. So each fermion interacts with Q other fermions, and the interaction strength, the J I1 to IQs, are chosen from a Gaussian ensemble with zero mean and variance, as I've shown on my slide. Okay, and this particular model in the IR limit, in the low energy limit, it can be shown that this model has emergent conformal symmetry. But as I move away from the IR limit, once I keep the finite energy corrections away from the low energy limit, then I see that this emergent conformal symmetry is broken both explicitly as well as spontaneously. And this leads to some soft mode physics, which I want to describe using this diagram here. So here, for example, in this diagram, G0 is some solution, the saddle point solution of the SYK model, which obeys the emergent conformal symmetry. So it's a solution in the deep IR. So when I apply the conformal transformations in one dimension, which is basically some arbitrary reparameterization of the one coordinate that I call time that you have, then there is no action cost associated with that particular application of that particular conformal reparameterization of the time. So that is demonstrated by the manifold or the curve on the upper side of the, I'm sorry, I can't really see my cursor here, so I would have liked to point out, but I can't really figure out how to point out here. But I guess you understand the plot on the curve on the top is like it's a schematic of all the solutions that you could generate by applying the reparameterizations, and there's absolutely no action cost associated as I move along these different solutions. So this is like the modular space of the SYK model. However, once I keep once I move away from the strict low energy limit and keep the finite energy corrections, which are measured by this parameter 1 over j. So j going to large is like the IR limit. So finite j corrections takes you away from the strict IR limit, and then your G0 gets modified. The solution G0 gets modified, and once you keep these solutions and then apply reparameterizations, then you move along a new manifold, which is this manifold that I'm showing, the second bottom manifold in my plot. And then there is an action cost associated, a soft action cost associated with the application of reparameterizations, which is known as the Schwarzian action. And the action is precisely the Schwarzian derivative, which is this complicated derivative of the f of tau reparameterizations that I apply on my to move along this orbit of solutions. I'm sorry. So right. Moreover, these low energy excitations are not the only excitations in the full spectrum of the SYK model. There is a discrete tower of states that also arises in this IR limit of the SYK model, and this tower of states is approximately equally spaced. So in full totality, there are two kinds of states in the spectrum of the SYK model. The low energy states, which are described by the Schwarzian action that I just talked about, and an excited, almost equally spaced discrete tower of states, which are known as which are related to the Majorana fermions of the SYK model through the bilinear form that I'm showing here. Okay, and the question that we want to understand, especially in the second part of our talk, second half of my talk, is how do these different states, which lead to, say, a black hole formation in the two-dimensional dual of the SYK model, and we will study both of these questions separately, how the excited states lead to formation of black holes, as well as how the low energy states lead to formation of black holes in the work that I'll be describing. So any questions in this brief lightning introduction to the SYK model?
Yeah, Pranjal, sorry, can you go back to the previous slide?
Yes. Yep.
Yeah, so can you say a little bit about the text below the two boxes using duality between 2D Liouville and Schwarzian theory and limit of conformal 6-point functions?
Right. So here I'm basically describing briefly what are the techniques that I will use to study these questions. So for the case of these low energy reparameterization modes, I will describe how these modes can be, how the Schwarzian action can be obtained as a dimensional reduction of a two-dimensional Liouville theory. And I will use this dimensional reduction, which I'm calling the duality on my slide here, to understand correlation functions in the Schwarzian theory, using the correlation functions in the two-dimensional Liouville theory, which is a very well studied and well understood subject. And on the right hand side, I'm saying that I will look at the correlation functions of the operators uh, of the kind ON. So I will be interested in 3-point functions of these operators ON to study eigenstate thermalization, and which would be same as studying the 6-point functions of these Majorana fermions. So yeah, so the text describes the techniques I'll be using to.
And also, what is the two boxes with ETH written on it? What is that supposed to indicate?
So the question that we are trying to, the question of whether for pure states in the bulk dual of the SYK model would be closely related to asking how pure states thermalize in the SYK model, and a way of understanding thermalization of pure states is eigenstate thermalization, describe said later as a part of my talk.
Okay, thanks.
Thanks. Okay. So let me go on to describe the ergodic limit of the SYK model before I move on to discussing the eigenstate thermalization. So the quantum ergodicity is a subject that has been studied quite extensively, but most of these studies have been numerical for a large class of models, and a very good book to study to understand quantum ergodicity and its application to various models, especially models which have dispersion in them, is this book by Efetov, and one can find a lot of references there which discuss various applications of quantum ergodicity to various systems, all of it numerical, in past 50 or 60 years. The quantum ergodicity has also been studied in relation to the SYK model through some numerical computations of various observables, including the spectral form factor and the operator 2-point functions, in various papers, starting with the work of Kotler et al. In 2016. And they find that the spectral statistics of the SYK model and the spectral form factor of the SYK model resembles closely that of the random matrix theory, which is a numerical evidence that there is ergodicity as I defined earlier in my talk, in the SYK model. But what we are interested is to understand whether I can have an analytic understanding of the emergence of quantum ergodicity in the SYK model. More precisely, can I describe microscopically more precisely where, in what regime, the spectrum of the SYK model starts resembling that of the random matrix theory. And part of my talk would be, the first part of my talk would be to try and understand this emergence of quantum ergodicity, and will be an extension to some existing literature. Okay, but before I delve into that, let me describe a very important tool that goes into studying the quantum ergodicity, which is the first quantized understanding of the Hamiltonian. So since we are interested in understanding the spectrum of the Hamiltonian that generates time translation, and my definition of the quantum ergodicity is in terms of the properties of this spectrum of the Hamiltonian, we need to understand how can we extract out the spectral properties of the Hamiltonian. So let me start with treating the Hamiltonian as a D by D matrix, where the D is the dimensionality of my Hilbert space. So whatever I'm saying here can be generalized immediately to even quantum field theories, where to be really precise, D is infinite, but then you could use your standard regularization schemes to think of D as D being finite, but the technology still applies to quantum field theories. So the idea is that I want to obtain the density of states of this Hamiltonian H, and the density of states is related to the Hamiltonian as imaginary part of, I'm sorry, I forget a trace here, so it should be trace of inverse of this particular combination of energy E and the Hamiltonian matrix H. So E here is basically just a number E multiplying a D by D unit matrix. Okay, and one way to obtain, since like for an arbitrary D by D matrix it's very hard to compute inverses, one way to compute like at least formally to compute the inverse is to introduce some auxiliary fields, which auxiliary fermions, which and then the inverse of this kernel E minus I epsilon minus H can be written as a path integral over these auxiliary fermions. Sorry, I have made another typo here. So apart from the exponential, there should be a psi bar in the pre-exponent of the path integral that I'm writing on the right hand side. Okay, so let me just write it like this. So here you have an additional psi bar. Okay, so that gives you basically the inverse of this kernel. Okay, so since I'll be going back, let me just clear this. Okay, sorry. Right. And here I'm using the tilde instead of an equality because the right hand side is an unnormalized path integral. Basically, you have some determinant of this kernel that should appear here, and I'm not writing that precisely. And there are many techniques that can be used to find out the the normalized inverse of this particular d by d matrix, and one of them is the replica technique. And ergodic limit of the S by K model was indeed studied using the replica path integral in this work of Atland and Bagretz. And what they computed was the 2-point function of the density of states at two different energies with separation omega. And they find a behavior which is very similar to that of the random matrix theory. And they obtain this in the limit where the energy in the spectrum of the S by K is high, and the omegas, the distances between the energies that are being studied is sufficiently small. Okay, and in this particular limit, they were able to obtain the spectral statistics which are exactly the same as that of the random matrix theory. So what I'm writing on the right hand side here on this particular equation is the 2-point function of the density of states in the of what I obtained in the random matrix theory with unitary symmetries. This is not all random matrix theories. It's one particular class of random
Pranjal,
matrix.
Rohan has a question.
Yeah.
Rohan, oh, he has put down his hand. Okay, fine.
Oh, sorry. Yeah.
Oh.
Yeah. So, Pranjal, when this particular computation was done for finite J or at the conformal point when you say for SYK model?
So this is done for finite J. So whatever I'm describing here does not need the quantum ergodicity study, does not need the strict higher limit of the SYK model. So in that way, it is much more robust, much more stronger results that hold true for generic SYK model.
Thanks.
You only need large N for this. Okay. So and from the study of the observables in the random matrix theory, we know that the one part in this 2-point function, the constant part of this 2-point function of the density of states is the part that gives rise to the slope and decay behavior at the starting times, and the sine kernel, the delta function minus the sine square x by x square part, is precisely the is the part that gives rise to the ramp and the plateau behavior in the observables. Okay, in their paper, they also find out the non-universal physics that takes you away from the RMT as some form of collective modes in the SYK model. So this is precisely where this quantum ergodicity breaks down, the spectral rigidity of the SYK model breaks down, its comparison from the SYK model breaks down. In this work, they gave us a very robust technique to try and understand the emergence of RMT statistics analytically within the SYK model. And in our work, we are trying to generalize this to study operator correlation functions in the SYK model. Okay. I wanted to just pause for a minute and ask Madhu if I answered the question that he was asking previously about understanding Hamiltonian as a d by d matrix.
Yeah, got it. Thanks.
Okay, thanks. Good. So what we are trying to do, what we have done in our present work, is to look at uh, the the effect of these spectral statistics on operator correlation functions within the SYK model. And for that, we are looking at this particular resolvent, which is which measures the matrix element, the operator elements, operator expectation values measured in two different states, separated by some energy omega, some two different energy eigenstates. So alpha and beta are some energy eigenstates separated by energy omega, which is imposed by the delta function in this definition of this spectral resolvent. And the reason we are interested in this is studying this resolvent is because this is related to the thermal two-point function, Fourier transform of the thermal two-point function that I described here, the trace of e to the power minus beta by 2h, O dagger e to the power minus beta by 2h, O. And I can do the Fourier transform of the spectral resolvent with respect to omega. So omega is the energy which is dual to the time that appears in the real-time behavior of this thermal two-point function. Yes, and I can obtain beta, the temperature beta, by analytically continuing the Fourier transform of the spectral resolvent to complex times. Okay. So what we find in our work is that the behavior of the spectral resolvent in the ergodic limit as defined in the work of Atland and Bagratz is given by this particular, the second equation on the right hand side. And what you see here is that when the energy differences between these energy eigenstates, when omega goes to 0, then then there is a disconnected contribution to the spectral resolvent, which is the trace of O times trace of O dagger. And when the gap between the energies is non-zero, then there's a connected contribution to the spectral resolvent, which comes from trace of O dagger. In the cases where O itself is an extensive operator, so the trace of O scales as dimension of the Hilbert space, what you can see here is that the first part is much more dominant than the second part. So the second part is like suppressed exponentially in entropy, or as 1 over dimension of the Hilbert space with respect to the first part. So this is something that we hope to be able to see in the numerical state. This can be like studied very well in the numerical studies of operator correlation function. Yes, Madhu, you had a question?
Yeah, no, this is from Lata. She asks, are the alpha and beta states time evolved states?
Oh, no. So these are like the energy eigenstates. So these, like, even the time evolution does not change them.
Lata, is that okay?
Yeah, okay. I was just trying to see the omega on the left hand side. It's after the Fourier transform, but I was just trying to understand that time dependence T on the left before the Fourier transform, if that's coming from alpha and beta, but he's saying no. So
no, so
it
does come from alpha and beta in a way. It comes from alpha and beta because it comes basically from omega. Like indeed there is some actually energies dependence, to be very honest. So like it also on the average energy of, so there's a difference energy and there's an average energy. So E alpha plus E beta by 2, there's a dependence on that. That's what I'm denoting by when I write the resolvent as a function of both E and omega. but in folded, there's a thing called folding of the spectrum, which takes into account the fact that you can take it into account the E dependence just by talking of the omega dependence of the resolvent. So it's something more complicated and something that we don't really need to go into detail of right now. So the important aspect here is that the omega is the variable that's conjugate to the time after the Fourier transform. So the real-time behavior really comes from how the resolvent behaves with respect to omega and not with respect to E.
Okay.
Actually, since I mentioned this, I'll just go back one more slide and talk briefly, just tell you about what this folding is. So you see the relation between the X variable and the omega variable is like X is omega times the density of states at energy E. Okay, so the E dependence completely comes from this multiplicative factor. Okay, so this is precisely the folding, and you see when you compute the resolvent, it only depends on X. So it has inherently a dependence on this E variable, but it's not really important in deciding the late time behaviors of the observables. Is that clear?
Yeah, not so much, but you should go on, please.
So okay, so what you should take away from what you should take away is just that the omega is the more important parameter. The difference between the energies of these energy eigenstate is what is more important here, and not where in spectrum you are.
Okay. Yeah.
So, okay, going back to this spectral resolvent, what we see here is that the sine kernel that appeared in the study of density 2-point functions, 2-point function of the density of states, also arises in the study of the correlation functions, the spectral resolvent, and the presence of this particular factor here will again give rise to the ramp and the plateau behavior that we expect to see in the ramp and the plateau behavior that we expect to see in the late time behaviors of these thermal correlation functions that we are interested in. Okay, and once again the initial decay will come from the connected part of these correlation function. So which is basically the first term in the expression of the in the spectrum of the spectral resolvent. And what we are presently doing is trying to understand how the non-universal modes of the SYK model eventually takes you away from the ergodic limit in the SYK model. That is like the part of the present work that we are doing. So that concludes my discussion of study of quantum ergodicity in this SYK model, and I would be happy to take any further questions that people might have. Okay, if not, then let me move on to this next part of the talk. In the next part of the talk, I will be interested in studying another aspect of thermalization using this model of SYK model. And in this study, what we are interested in asking is the second question that I emphasized earlier, which is how is it that when we start with pure states, we see thermal behavior in certain quantum systems, and we expect to improve our understanding of this question through through understanding the eigenstate thermalization hypothesis in the SYK model. So let me begin with a review of what eigenstate thermalization hypothesis is in general. Okay, also before I proceed, how much time do I have?
So
Madhu?
it's 4 now, and so maybe try and wrap it up in 20 minutes. That seems viable.
Okay, yeah, that seems viable.
Okay, so that we have some time for questions also at the end.
Yeah. That's good. That's good. So, so the understanding of thermalization, how a system thermalizes, is difficult even in classical system, and we have a putative understanding of the thermalization even in classical systems using the ergodicity hypothesis, which in turn is understood to arise out of chaotic behavior of some complex systems in classical classical mechanics. However, there is also another way of defining, even within classical system, thermalization, which deals with studying the expectation values of certain operators in some typical configurations within the phase space of a classical system. And it states that the expectation value of observables in some typical configurations, classical configurations, should resemble or should be very close to the thermal expectation value. And it is this definition which gets readily generalized to the quantum systems, quantum mechanics, in form of eigenstate thermalization hypothesis, which states that when you measure a typical operator, and this operator is not extensive, non-extensive typical operator in energy eigenstates of a sufficiently complex quantum system, then it behaves in a fashion such that it's the matrix elements, when measured in the energy eigenstate basis, has a peak around the diagonal, and the diagonal values are precisely given by the microcanonical expectation values of the operator at that given, corresponding to the microcanonical expectation value at that given energy. Okay, and there are corrections both of the diagonal values and as well as the off diagonal values of this operator in the energy eigenbasis. But these off diagonal elements and the corrections of the diagonal values are suppressed exponentially in the microcanonical entropy. And this is the hypothesis. The hypothesis says that any system and any set of operators which behave in this particular fashion can be shown to thermalize by dephasing for more general class of states within this quantum system. So this is a way that we can try and explain the emergence of thermalization in a generic many-body quantum system. And what we want to do is to see whether this hypothesis is valid for quantum systems that we are interested in. So if this hypothesis is true, then basically we understand how pure states lead to thermalization in a quantum system. And that's what we'll be trying to do for the SYK model in this later part of my talk. Okay. But before that, we want to generalize this hypothesis for a more general class of operators. And the simplest generalization would be for the case of an arbitrary k number of insertions and measuring the expectation value of k K operators in pure energy eigenstates. This obeys eigenstate thermalization in the same sense that these expectation values peak along the diagonals and the off-diagonal elements are exponentially suppressed as long as K is not K does not scale with the dimension of the Hilbert space of your quantum system. So as long as the combination of these K operators is non-extensive, then we expect to see eigenstate thermalization hypothesis. And in particular, there is a generalization that was first conjectured by my collaborators in their work, which states that when you measure out of time ordered correlation functions in pure energy eigenstates, then you should see the exponential growth that you observe when the same OTOCs are measured in thermal ensembles. So, and in this case, the coefficient of the exponential growth, the Lyapunov coefficient, the lambda of L, is given in terms of the temperature. It's bounded by this temperature beta, which can be obtained by the equivalence of ensemble. So if I have the energies of these states M to be E bar, then through the equivalence of microcanonical and canonical ensemble, I can read out a temperature that corresponds to these energies, and the Lyapunov exponent for especially holographic CFTs is given in terms of this temperature 2 pi by beta. Okay. For the case of conformal field theories, we can again use the state operator correspondence, which relates every energy eigenstate with an insertion of an operator, and we can describe the eigenstate thermalization hypothesis as a correlation function. So eigenstate thermalization hypothesis for K operator insertions can be understood as a behavior of K plus 2-dimensional correlation function within this conformal field theory in vacuum state, and we expect that these correlation functions would also show ETH kind of behavior in general. For the particular case of 3-point function, this constrains your OP coefficients to behave in such a fashion that there is, when two of the operators are heavy and one is light, then the OP coefficients have a peak when two of these heavy operators are the same, and the OP coefficients for all other cases are exponentially smaller compared to the OP coefficients when two of these heavy operators are the same. So these are like the more generalizations of eigenstate thermalization hypothesis to study this hypothesis in a more general quantum system. Okay. And we'll be using this to study ETH in the SYK model. Okay. So let me start with the initial motivation of the eigenstate thermalization that arose out of the numerical studies of my collaborators. So they studied eigenstate thermalization in a particular version of SYK model which involved complex fermions and had a finite number of n. So they studied this particular version of SYK model numerically through exact diagonalization. They saw that they verified that the eigenstate thermalization hypothesis holds true for this particular version of SYK model. And in particular, they looked at the expectation of the number operator at a given site in pure energy eigenstates, and they found that there is a peak in the expectation of the operator values operator elements in this energy eigenbasis along the diagonal. Okay, and the diagonal value matches those that one would, the values that one would obtain in the microcanonical ensemble. Furthermore, they also looked at the off-diagonal elements of these, and then they found that they also have some they are exponentially suppressed with respect to the diagonal elements, and they are largely constant for a window of omega, but start deviating from the constant values. So there's and the constant value is basically the region where these are constant is basically the region where RMT holds true. So the first part of my talk is basically our attempt to understand these deviations from the RMT like behavior. And the second part of my talk would be to obtain the diagonal values themselves analytically within the SYK model. Okay. So this work was a motivation in trying to attempt and understand the eigenstate thermalization analytically in the SYK model. What these people also did was look at the out-of-time ordered correlation functions in pure energy eigenstates and compared it to the thermal expectation values of these OTOCs. And then they find that the behavior is very similar, which is to say that OTOCs also show thermalization in pure states. And they conjecture that the Lyapunov exponent is given by the temperature that one obtains from the equivalence of ensembles is also correct numerically. So we would go on and try to understand these behaviors analytically. Good. So now let me start with obtaining analytically the eigenstate thermalization in the Schwarzian limit. So what is, so in general, when we compute correlation functions within the within this model, then the correlation function get contributions from both parts of the spectrum that I had described earlier in my introduction of the SYK model. So basically they obtain contributions from the exchange of Schwarzian modes, as well as they obtain the contributions from the exchange of these excited states of the SYK model. And I will begin with describing the contribution from the exchange of Schwarzian modes. So the Schwarzian theory, let's go back and recall what it was. So the Schwarzian path integral arose from moving away from the conformal limit of the SYK model by considering the 1/j corrections. And as I apply the reparameterizations on my time coordinates, I get an effective action which is given by the Schwarzian action. And when we want to understand what happens to the correlation, what's the behavior of the correlation functions in the SYK model, when we account only the contribution of these low energy modes, okay, which are known as the pseudo Goldstone modes. And we can do this by looking at correlation function of the operator and applying reparameterization on these correlation functions, and then doing the Schwarzian path integral after the application of the reparameterization modes. So this appears within the Schwarzian theory as an insertion of some correlation functions within the pre-exponent within the Schwarzian path integral. So this is the problem that we are interested in studying right now. Okay. The interest in Schwarzian theory is more than just the SYK model, because the Schwarzian theory can be shown to arise in the low energy limit in a larger class of models that have been studied in the past few years. Basically, the tensor models, which have low energy physics very similar to that of the SYK model. It also arises, like the Schwarzian theory is also the dual of the two-dimensional gravity, which is the Jacob-Teitelbaum gravity. So that's also why the study of Schwarzian theory as a standalone theory is interesting. And the Schwarzian theory also arises in the near horizon limit of extremal black holes. So which makes it an interesting theory to study to understand the low energy limit of high dimensional theories, especially the holographic theories. And well, the best reason to study a standalone Schwarzian theory is also because it's quite tractable, as we will see briefly. Okay, so I want to show that the Schwarzian theory can be obtained as a dimensional reduction of a two-dimensional Liouville theory studied on an open string with a more general class of boundary conditions. Okay, so the boundary conditions that I impose on the two ends of the open string need to be consistent with conformal symmetry, and there is a class of boundary conditions that I can impose, which are the Dirichlet and the Neumann boundary conditions on these boundaries. One needs to notice that the Dirichlet boundary condition for the Liouville theory is really the field taking an infinite value at the boundary. And the Neumann boundary condition is not just that the derivative of the field vanishes, but there's a more general class of Neumann boundary conditions which are consistent with conformal symmetry and are given in terms of this parameter R, which appears on the right hand side. Okay. So these boundary conditions can be consistently imposed by modifying our path integral of the Liouville theory by introducing some boundary terms, and then studying the Liouville theory with the inclusion of these boundary terms. Okay, so then, like, this is a subject. When we look at the subject of the Liouville theory, which is solutions of the Liouville theory is a very well studied subject and can be classified into various categories. When we impose the Dirichlet boundary condition at both ends of the open string, then we get only parabolic solutions. This is a particular classification of solution that we don't really need to go into the detail of. However, when we impose both Dirichlet and Neumann boundary conditions, like one at each end, then we find a more general class of classical solutions of the Liouville theory, which are classified as elliptic, parabolic, and hyperbolic solutions. So the reason I'm throwing out these more complicated words here is because what I'll find is that the thermal behavior of different pure states in the SYK model will be related to the different classes of the solutions of the Liouville theory. So yes, so now starting with the Liouville path integral in two dimensions, I can perform dimensional reduction as well as, when I perform a dimensional reduction of the Euclidean time-like direction, as well as take the classical limit, which corresponds to taking the central charge of the theory to infinity, and the central charge is related to this parameter b as 1 over b square. That gives rise to the Schwarzian theory in the dimensionally reduced one-dimensional system. Okay, and depending on what boundary conditions you impose, you may or may not have some additional insertions within the Schwarzian path integral. Okay, so this is a very nice way of obtaining the Schwarzian path integral from a theory, two-dimensional Liouville theory, which is very well understood. And the computations in which are easier than doing the computations directly in the Schwarzian theory. So what we find is that when we do the dimensional reduction of the Dirichlet case, then we end up with a Schwarzian theory for a one-dimensional model, one-dimensional Schwarzian theory, which corresponds to a finite temperature theory. Okay, and these the temperature of this dimensionally reduced theory is precisely the size of the open string that we started with, and is given in terms of beta. However, as I just mentioned, when you have like a Dirichlet and a Neumann boundary condition, then the dimensionally reduced path integral has an additional insertion in the Schwarzian path integral, and this additional insertion basically breaks the symmetry from diffeomorphism, the full reparametrization symmetry, to reparametrization mod U1 instead of reparametrization mod SL2R, which is what happens in the more general in the finite temperature good old Schwarzian theory. Okay, and the idea is to interpret this operator insertion within the Schwarzian path integral as creating a pure state of the Schwarzian theory, of which we want to understand the thermal behavior. Okay. Moreover, the vertex operators of the Liouville theory, after the dimensional reduction, reduced to these bilocal operators in the Schwarzian theory. And the multilocal operators in the Schwarzian theories are the only physical observables that I can study within the Schwarzian theory. Okay. From the SYK point of view, these operators are basically the 2-point functions of, say, the excited operators in the excited spectrum of the SYK model. But within the Schwarzian theory, I just can consistently study such 2-point non-local operators within the Schwarzian theory. Okay. So just to summarize in terms of pictures, what I have here is, when I'm interested in studying the correlation functions of these bilocal operators, for example, in the Schwarzian theory, then it is same as the insertion of some operators, some local operators in the two-dimensional Liouville theory and performing a dimensional reduction. Okay, and the correlation functions of the 2-point function, correlation functions of operators in Liouville theory is very well studied. We know their behavior, and so therefore the question of these correlation functions within the Schwarzian theory becomes much easier when we look directly at the correlation functions in the Liouville theory and perform this dimensional reduction and the classical limit. And using this technique, what we find is that the states corresponding to the parabolic class of the two-dimensional Liouville theory are the states that actually thermalize in the one-dimensional Schwarzian theory, and so do the elliptic states in the dimensional reduction. However, the hyperbolic states don't thermalize in general. Okay, there's an additional class of parabolic states that can be created by insertion of these excited within the Schwarzian theory. And what we find is that these parabolic states thermalize, but with some subtleties, which is to say that these parabolic states thermalize weakly. So if you have a background temperature, then the insertion of these operators O, L of H increases the background temperature. But if you don't have any background temperature, then you don't see any thermalization. So there are also a class of states which provide some kind of weak thermalization within the Schwarzian theory. Okay. So that concludes my study of ETH in the Schwarzian limit. I have a very small last section of study of ETH in the conformal limit. And I think I can just do that in last 3 minutes that I have. So what I'm interested in is also considering the contribution of the excited states to the correlation function. And in this particular study, we are only we are completely disregarding the contribution of the Schwarzian modes. We are only considering the excited modes, and these can be studied by looking at the 3-point functions of these operators in the SYK model in the conformal limit without the contribution of Schwarzian modes, and study a particular limit in which 2 of these operators are heavy, their weights is scaled to infinity, while the third operator is of energy of the order 1. And what we find is that in this particular case, the eigenstate thermalization hypothesis holds true, because when we look at the OP coefficient of these 3 operators in the conformal limit, then this has precisely the form that one expects for the eigenstate thermalization. So that kind of, without going into the details, that kind of summarizes my talk, and I can take more questions here.
Okay, thanks a lot, Pranjal. Are there any questions? Yeah, Rohan, go ahead.
Pranjal, can you go back to your Schwarzian understanding of your
Yes.
Schwarzian analysis before this?
Yes.
Before, yeah, this slide. So when you have Dirichlet Neumann condition, you have this. You do not have this SL2R, right? I mean, you have this U1, which is the symmetry, and
Yes.
so basically, what you have done, you've taken the solutions and computed out of time ordered correlators.
Yes.
To compute the Lyapunov exponent.
Yes.
And so there for research, so can you, so for one particular parabolic class, you do get lambda to be 2 pi by beta.
Yes.
The first one. So so there is this chaotic behavior, although there is no SL2R symmetry.
Yes.
So usually we would have thought that it is this Schwarzian, the behavior of the Schwarzian propagator when you compute corrections to the 2-point or to the 4-point function that contributes to this exponential growth, right?
Mm-hmm.
So, but you're saying that even if you have a perturbation to it which breaks this SL2R symmetry, you still get the Lyapunov exponent.
Yes. Yes.
That's a good thing. Okay, fine. Another thing is, you mentioned Soner and Vielma's paper of 17, and there you made a point that they try to conjecture this comparison, this specific comparison. Can you explain clearly what exactly they are comparing and saying?
So they.
Yeah. So as I understood it, are they trying to say that if you had done an RMT analysis, you can read off the Lyapunov exponent in a particular manner? Is it?
No. So here, what they're doing is they're doing here not for RMT, for SYK. They look at OTOC for the SYK model, but instead of computing OTOC in a thermal ensemble, canonical ensemble, they compute it in pure energy eigenstates. Okay. And then they compare it to the OTOC way of the OTOC that you would get in a canonical ensemble at a temperature beta. Okay, and they try to read off what value of for what value of beta the two match. Okay, and they find that the value of beta for which they match is the one that you would get by, okay, I've not written it here, is the one by that you obtain by equivalence of ensemble. So if you have a macrocanonical ensemble at energy E, it is also equivalent to some canonical ensemble at some temperature beta, and that equivalence gives you a relationship between beta and E. Beta is a function of E. So they find that that same beta is what appears in the Lyapunov exponents of the OTOX when computed in pure state.
Okay, thanks.
Okay. Actually, I didn't mention it here. So this is another thing that we did analytically within the Schwarzian theory. Okay. What we did was also compute OTOX in these particular pure states of the Schwarzian theory that I define here. And we find that analytically these OTOX have an exponentially growing behavior. And the Lyapunov exponent is given by 2 pi by beta, and the temperature beta here will be the same as what you would get by equivalence of ensembles, which is to say that suppose you compute just a 2-point function as I was showing here. So this 2-point function itself behaves thermally in this particular limit that I'm talking about. Okay, so that the temperature that you read off from the 2-point function is precisely the same temperature that enters the OTOC Lyapunov exponent.
Yeah.
Excuse
me. Yeah. Okay, thanks.
Any other questions?
Just hold on, Pranjal. What? So some of these will also hold in the Dirichlet case, right?
In the Dirichlet case, yes.
Yeah. And why is Dirichlet-Neumann case more this thing? You said that because when you're slightly broken it, you have U1 instead of SL2R.
Instead of
you made a you made a statement about why we are looking at the Dirichlet-Neumann case because it
right, because I want to create, so I can create pure states only using the Dirichlet-Neumann case, like a more general class of pure states. So I interpret this operator insertion. So see, you can see immediately why this operator insertion breaks the symmetry to U1, because then you have only the translation symmetry. Okay. Now, in this, I interpret this operator as an operator which is inserted at minus beta by 2 and plus beta by 2. Okay. Which is precisely how it actually appears. When you do the dimensional reduction, I'm demonstrating it as a 1 insertion here, but what it really appears during the dimensional reduction is a square root of what I'm demonstrating here, like this 4 pi by c upon beta tan pi theta term, f prime beta by 2 term.
Oh, so that particular thing you will interpret as a operator insertion.
Yes. So that is the operator, because that's a local insertion within the Schwarzian path integral. It does not depend on sigma.
Okay.
There's no sigma integral involved with that. So that's a local insertion.
So after the insertion, you have broken down this thing to SL2R. So there are no more, and it is, so you will directly get your, what is the generating function for these operators on the field.
Yes.
Okay, fine.
And then, like, the important thing is to take the beta. So I want to remove this background temperature beta here. I want to look at these states when beta goes to infinity. So when you have this insertion here and you interpret it as half of it inserted at minus beta by 2 and half of it inserted at beta by 2, then you can take beta going to infinity limit, and then you end up with a pure state, not a thermal state, at plus infinity and minus infinity. And you ask whether this pure state thermalizes or not. And what we find here in this table is that after that procedure, there is thermalization in that state. Like the correlation functions are thermal even after taking beta going to infinity.
Okay. Thanks.
There any other questions?
Yeah, can I ask one quick question?
Sure, go ahead.
Yes.
Yeah, so Pranjal, the density 2-point correlator that you, 2-point expectation that you showed for ramp plateau and then dip ramp plateau structure. So that looks, with the sine square, that looks very similar to a GUE SFF, whereas this paper on random matrix behavior of SYK, they have a dependency on N, which kind of random matrix behavior you will have, whereas you have no dependency on N in this formula. So it looks like for all N's, you have the same density correlator.
Not really, because I didn't mention it, but we are looking at those classes of N for which it is the symmetry class is unitary.
So for which it falls in the GUE class.
Yes, yes. So this
okay,
is consistent with that classification of SYK model.
So for other classes, then do you also have a expression there?
We have not checked it. Because GUE, like obtaining GUE using these techniques is easiest in my understanding. So that's why we did it only for GUE. So this is what Atlan Bagritz did, and we kind of follow their suit and do it only for the unitary class.
Okay, yeah, okay, thanks.
I have a very vague question. Like at some point, I think you mentioned about 6-point functions, analyzing 6-point functions. So, I mean, can you just, like what was the,
So the comment was this, that in this last part where I'm looking at the excited modes, I'm looking at the 3-point function of these operators O, right? So these O are themselves bilinear. So in terms of the fermions, Majorana fermions, it's a 6-point function. So you can the way these correlation functions are computed is you start with a 6-point function of fermions and take the coincident limits when 3 pairs of 2 fermions approach each other.
Some OP limit, you mean?
Yes.
I see. All right.
It's not really an OP limit in the sense that you really want these 2 fermions to lie on top of each other. Right? That's the way the operator is defined here.
Right. It's not an OP because it's a bilinear. It's like 2 operators are at the same place basically. It's not like in the limit x1 goes to x2 psi x1 psi x2. Not that kind of a this thing, right? I mean, this is not the operator. It's literally psi x1 psi x psi bar x. Like it's at the. I understand what you mean. Yeah, it's not OP limit. Yeah, all right.
Any other questions? I've noticed that it's the always the usual suspects asking questions. So if there's questions from not the usual suspects, please feel free to.
Only the usual suspects remain as of now, as you can see from the participant list.
Did you watch the usual suspects over lockdown?
All are here. Okay. Nice.
Okay, if there are no more questions, then let's all unmute temporarily and thank Pran.
Thank you.
Yeah, very good talk.
Yes, very, very nice talk.
Yeah.
Oh, thanks.
One second, let me stop recording and then we can make fun of it.
You can clap and it can all unmute and clap together, right?
That's what I suggested, but once again, let me stop recording.
I was clapping, no one like.
I was clapping.
I clapped. This is my
I
clap.
was clapping.
I was also clapping.
Okay, I'm going to stop recording now. Hold on one second.